In this lecture, I will introduce the use of hyperbolic graph embeddings in learning representations for graphs that exhibit certain hierarchical and tree-like structure. Um, so in previous lecture, we have focused on graph representation learning in the Euclidean space, which is the R to the N. However, Euclidean embeddings cannot always capture complex graph structure. So here we have an example of a tree structure, a complete binary tree, where the first level we observe there's one node, and the second level we have two nodes, and the third level we have four nodes, etc. So in this kind of tree-like structure, often there is an exponential increase in the number of nodes as the depth of the tree increases. So these kind of trees are difficult to be embedded in the Euclidean space, as you have seen, because the slide itself is a 2D plane, and we can see that as the depth increases, the nodes that are leaves become closer and closer to each other to the point that they can no longer, the embedding space could no longer represent the distance between them faithfully, because they are very, very clustered together due to the exponential increase in the number of nodes. So here we are focusing on these kind of graphs with such tree-like structure. So we define these kind of tree-like graphs as graphs that are similar to a tree, for example, the binary tree as shown above, but it can still contain very few cycles. For example, in real-life situations, we can have things like knowledge graph that are organized hierarchically because many of the human knowledge are organized hierarchically, and at the same time, there could still exist a certain kind of loops in this structure. So it's mostly a tree, but with a certain number of loops in the graph itself. So here, we're considering this kind of structure, and we want to note that embedding geometry has been very important in terms of capturing this kind of special graph structure. Here we consider some other interesting graph structure. For example, if we have a graphs with many very large cycles, these kind of graphs are best embedded into spherical geometry, because in a spherical geometry with a positive curvature, the graphs we can naturally embed many cycles because the sphere contains many cycles. Whereas if we have a grid-like graph, a Euclidean space is the best because, as you can see, the Cartesian coordinate itself is a grid-like structure. So a Euclidean space with zero curvature would be the best. So how about hierarchical and tree-like graphs? For these kind of graphs, we're considering the use of hyperbolic space, which is an alternative embedding space to model embeddings for trees with tree-like structure. The advantage of hyperbolic embedding space allows it to naturally model trees, and we will elaborate on these advantages in the later slides where we explain the definition. However, there are certain challenges when we combine deep learning and hyperbolic spaces. The primary reason is that existing deep learning toolboxes can only be applied to a Euclidean space, whereas in hyperbolic space, we need to define special operators to perform these kind of deep learning operations. Let's first define what is a hyperbolic space. So hyperbolic geometry differs from Euclidean geometry by its fifth axiom of Euclidean geometry, which is the parallel postulate. So in Euclidean geometry, the parallel postulate says that in a given plane, given a line and a point that is not on the line itself, at most one line parallel to the given line can be drawn through the point. And this seems very obvious in the Euclidean space. If we have a line, then the line parallel to itself is kind of unique if we only consider lines that pass through one point. However, in hyperbolic geometry, there are infinite number of lines that are parallel to a given line through the point. This might not seem very intuitive because we are very familiar with Euclidean space, but here is a representation of a hyperbolic space in terms of Poincare ball. So we will explain what is Poincare ball later, but it's basically a way to visualize the hyperbolic space in Euclidean space. And you can see the blue line here. It looks like a curve, but it is actually a straight line in the hyperbolic space. And we can also define a red point here, which is another point that is not on the line. In hyperbolic geometry states that there are infinite number of lines that are parallel to the line, and these lines are actually drawn in the visualization. So all these curved black lines that we draw here, they're actually straight lines in hyperbolic geometry, and they also pass through the red point. And at the same time, they are also parallel to the blue curve. To the blue straight line in the hyperbolic space. That's mainly how it differs from the Euclidean space. So because of this spectral properties, hyperbolic space cannot be naturally represented in the Euclidean space because it violates the fifth axiom of Euclidean space, which is the parallel postulate. So we commonly use two geometry models to represent or to visualize hyperbolic space by embedding it as a subspace of the Euclidean space. And they are also equivalent. So we can also map between these two models that visualize hyperbolic space in Euclidean space. So the first model that we're going to introduce is the Poincare model. This is a model where we represent the hyperbolic space as an open ball. So a visualization of it is on the right, where we can see a ball. And this, by open, we mean that the set of all points in this hyperbolic space do not include the boundary of the ball. So the outer circle is not part of the ball, but everything inside the circle is part of the Poincare ball. And the radius is proportional to the square root of k. And we will introduce what is k later. K is actually the inverse of the curvature. And the important property here is that each triangle in the figure has the same area. So it might not, again, it's not very intuitive in the Euclidean space, as we see like all the triangles in the middle tend to have a larger, seems to have a larger area in the Euclidean definition of Euclidean metric. But every triangle here actually have the same area. And you can see why this space is very amenable to embedded hierarchical or tree-like structure, because you notice that in the middle or in the center of the Poincare ball, there are very few of these triangles that are in a hyperbolic space, whereas towards the edge of the circle, you can see like there are exponentially many of these small triangles, albeit with the same area, that are embedded towards the edge of the hyperbolic space, or towards the edge of the Poincare ball. So this exponential increase in terms of the area or the volume as the radius or the norm increases, allow us to embed hyperbolic trees. So basically trees can be embedded by embedding its root in the center, because there are very few of them, and embedding all the leaves on the edge of the Poincare ball, because there are exponentially many of these leaves as the depth increases. And we're going to introduce another alternative model that models the hyperbolic space, which is called the hyperbolic model, and also called Lorentz model. This is basically an upper sheet of a two-sheet hyperboloid, and that is visualized in the figure below. And this is also a set of Euclidean space. So unlike the Poincare model, as you can see, there are exponentially many triangles towards the edge of the Poincare ball. Here, hyperbolic model is numerically more stable, meaning that you don't have to have extremely high machine precision to represent all these small triangles in terms of their embeddings towards the edge of the Poincare ball. Here, it is basically a hyperboloid, and there is no upper bound, so it can go. The numbers can grow very large, but it does not require very high number of floating point precisions to represent the exponentially many points that are towards the edge of the Poincare ball. So papers have shown that hyperbolic model is numerically more stable, and it also have the advantage of having a slightly simpler formula to represent its metric and as well as distances in this hyperbolic model. So a lot of times we do derivation and we represent the neural network architecture inside this hyperbolic model. So these two are, so the Poincare ball and the hyperbolic model, these two are equivalent in the sense that we can have a mapping that are between the Poincare ball and the hyperboloid. And this mapping is 1-to-1. So it's a bijection. So given the brief introduction of the hyperbolic space, we want to also define our task here. So the task is the typical graph representation learning, which we have learned throughout this lecture. And tasks could be things like link prediction or node classification. And an example example embedding space that achieves this kind of task is the Poincare embedding by Nico in 2018. So in this visualization, which is in the form of a Poincare ball, we can see that entities are embedded inside this Poincare ball. And towards the center of it is they contain the nodes with very high hierarchy, or nodes that are towards the root of the tree. So for example, we have entities, we have a physical entity, we have abstraction, organism. These are all very abstract and high-level nodes that can contain many, many different childrens. And towards the edge of the embedding space, there are many, many different, exponentially many entities can be embedded there. And these are typically nodes that are in the lower hierarchy or towards the leaves of the tree-like graphs. For example, things like arrival, metabolic rates. These are very concrete and very detailed description of certain entity. And there are exponentially many of them, which can be embedded towards the edge of the Poincare ball. And this is basically the kind of embedding we want to achieve so that we can perform things like link prediction, which means we can predict whether an entity and another entity in this knowledge graph are connected, meaning that for example, whether the bread and food are connected. It could be connected through a hierarchical relation, or it could be connected through a non-hierarchical relation. So this is link prediction, and we can also perform node classification by predicting a label for each of these nodes in the graph. Okay, and before going into the detailed architecture, let's first also look into how hyperbolic space are mathematically represented. So formal definition of the hyperbolic geometry is a manifold, which is basically a high-dimensional surface, a 2D surface, but in high dimensional. And a Riemannian manifold is a special manifold which is equipped with two things. One is the inner product. So the inner product between 2 points have to be defined, and it will define a metric space, or like how distances are computed in this Riemannian manifold. And the other thing that is necessary for a Riemannian manifold is the tangent space, which is a Euclidean space that approximates the manifold, but only locally. So you can imagine it is a tangent to the surface at a certain point, touching the surface at a certain point x. Both functions has to, Riemannian manifold states that both functions, which is the inner product and the tangent space, has to vary smoothly, or called differentiable on the manifold. There are also other concepts that are needed. So here we also consider the geodesics. Geodesics is defined as the shortest path in the manifold, which is analogous to the straight line in Rn. So if you remember the plot where we have the parallel postulate in hyperbolic space, all these curves are actually geodesics. So they are the shortest path between 2 points in the manifold. And that's why we can say that there are infinitely many straight lines passing through the point that are parallel to a given line. The hyperbolic space is a Riemannian manifold with a constant negative curvature. Here we represent it as -1/k, where k has to be greater than 0. So as you can see, when k becomes very, very large, the hyperbolic space curvature becomes very, very close to zero, and zero just means a flat space. So it will become more and more Euclidean as the as k increases. But the more negative is the curvature, so when k is small, the more curved the space will be. And here we look at a little bit of how does the curvature affect the embedding space. So we use negative 1 over k to denote the curvature, and root k is also the radius of the Poincare ball, and that's how the radius is related to the curvature. So if we look at the hyperboloid model, the formula is actually very simple. So this is the inner product definition, which is also called the Minkowski inner product in hyperbolic space. So if we have a d-dimensional hyperbolic space, the hyperboloid model will have a d+1 dimension, and the inner product is defined by these two things. So there is the negative part of the inner product, and there is also the positive part of the inner product, which behaves almost identical to the Euclidean component, but we also have the negative part, which is which has a negative sign in this inner product. And based on this inner product definition, the distance between two hyperbolic points can be computed as such. So given 2 points x and y in the hyperbolic space, we can compute this Minkowski inner product and divide by k, which is related to the curvature. And the r cosh means the inverse of the hyperbolic cosine function. So we use this function to compute the distance between 2 points. And another important concept is called the tangent space. So as we mentioned, that tangent space is basically a Euclidean Euclidean approximation on a local point of the manifold. So a local neighborhood of the manifold, we can have a Euclidean space that is tangent to the manifold, but only touching the manifold at this one point. So for example, in this visualization, we have this hyperboloid model again, representing the hyperbolic space, and the tangent space at the North Pole, which is the bottom of the hyperboloid, is drawn over here. And we can define certain mapping here. So this line, this is actually a straight line. Of course, it looks like a curve in the hyperbolic space, but if we also map it to the tangent space, this becomes a straight line because the tangent space is the Euclidean space. And the tangent space is defined again through this Minkowski inner product, where if we do inner product between v and x, it is 0. So that is that defines the set of all points v such that the inner product between v and x equals to 0 defines the entire tangent space at the point x. And finally, we discuss a little bit about geodesic distances. Geodesic distance, as we mentioned, is analogous to the shortest path in the Euclidean space, and is also the concept of straight line in the hyperbolic space. And the more negative the curvature, the more the geodesics will bend inwards towards the center. So, and the distance between 2 points will also increase. So here is an example plot where we compute distance between 2 points, x and y, with the same coordinate. So say, like imagine something like x is 0.5, 0.6, y is 0.2, 0.3, and the distance between them actually increases if the curvature increases. If the curvature becomes more negative. So towards the more negative parts, the distance between them actually increases more. So it can be more visualized in this figure, where we have these 2 points here, x and y, in the hyperbolic space. Here we just represent it in the Poincare ball, and here 0 is the origin. Root k is the radius, which is also inversely proportional to the curvature of the space. And the dark blue curve means is the boundary of the hyperbolic space where the curvature is more negative, right? The more negative the curvature is, the smaller the radius will be. So you can see that the geodesics are also drawn here. So if the in the dark blue, so in a higher curvature space, the geodesics is more bent towards the center, of the hyperbolic space, whereas for the lighter blue version, or the lighter blue space, which has larger curvature, the geodesics is less bent inward. And in the extreme case where the the space is Euclidean, meaning that the Poincare ball is kind of infinitely large, then the geodesics does not bend at all, which recovers our Euclidean concept of shortest path, which is basically a straight line here. And another important concept based on all these definitions is the exponential and logarithmic map. So this is a map that we can map from the tangent space to the manifold and vice versa. So the exponential map maps any point in the tangent space to the Euclidean, from the tangent space to the Euclidean, from the Euclidean tangent space to the hyperbolic manifold, and the logarithmic map maps from the manifold back to the Euclidean tangent space. So here it is a visualization, and we use the norm to represent the inner product between 2 points using this special Minkowski inner product definition. So we can conceptually visualize it as we have a V in the tangent space of X, and if we were to map it back to the hyperbolic space, it becomes the point Y, which is on the hyperbolic space. And inversely, we can use logarithmic map to map from this Y, the blue point, back to the red point V, which is in the Euclidean space, is a Euclidean coordinate in the tangent space of X. So here, this notation, we use X here as the point that is touching. So the tangent space of X is the Euclidean space that we want to map to and from, and K is the curvature. So it is the inverse of the curvature that we have defined. And here, notice that we have to use this Cauchy and Singe function, which are the hyperbolic trigonometry here. The formulas are really very complicated, the high-level concept is that there exists. You just need to know that there exists such mapping between the tangent space as well as the manifold, and we can use such mapping to perform operation in the Euclidean space and map it back to the hyperbolic space. So given all these preliminaries, we can now introduce the hyperbolic GNN. So the main challenge that we are focusing on here is that input features are usually Euclidean, but we want to map it to the hyperbolic space to compute the node embedding on the hyperbolic space. And the second challenge is that we need to perform aggregation in the hyperbolic space so that we can perform message passing. And the third challenge is that we do not know what is the right amount of curvature for the hyperbolic space that can perfectly embed the graph. So this is also something that we need to learn in the meantime. So if you recall, the GNN formulation is mostly very similar. So here is an outline of the GNN architecture, where we first compute the messages between all the neighbors as well as the center node, and then we aggregate all your neighbors' messages to compute a representation, the hidden representation after the aggregation. And finally, we will make an update of the representation so that the next level representation will capture the information of the previous layer representation. So this will be the typical like message aggregation and update function, but in the hyperbolic space. So note that here we are writing some superscripts, for example, like KL-1. So this will indicate the curvature or the inverse of curvature at the layer L-1. And here it is KL-1, KL, meaning that the update function needs to convert the point from the hyperbolic space of the previous layer, so in the layer L-1 to the hyperbolic space of layer L. And the high-level concept is also visualized in the figure here. So we have a bunch of points which are the previous layer embedding of the graph in the previous hyperbolic space, and we perform a message computation of these between these points as well as this center point here. And after we perform these messages, we need to aggregate all these messages. And we perform this aggregation in this tangent space of the hyperbolic space, because there is no natural definition of neural network operations in the hyperbolic space. But if we map them into the tangent space, then we can do something like a center of gravity inside this tangent space at the point X. So we perform this aggregation in the tangent space. And after the aggregation, we have the green point here, which is then mapped back to the another hyperbolic space of a different curvature. So you notice that here it is the layer layer L+1, and in the previous layer, it will be layer L. So this is a completely different hyperbolic space with a different curvature that but we can use the exponential and logarithm map to map the aggregated results back to the hyperbolic points in the new embedding space, with a different curvature. So the formula for all these computations are very complex, and understanding them requires like a entire lecture on differential geometry. So I won't go very much into the detail, but there are some high-level concepts that you can get from here. So for example, in the message computation, because hyperbolic space has no natural neural network operations that can be defined here, we can use this linear and linear layer, basically the linear and addition of the bias term in the tangent space of the hyperbolic space. So here we use this circle and multiply to represent this, like multiply all the linear operation, and this circle and plus inside it to represent the addition, so the Mobius addition. And these are very, and as you can see, these are defined through this exponential and logarithmic map here. So we first use the logarithmic map to map the point, the hyperbolic point, to the Euclidean tangent space on that point, on the origin. So here this O means origin. So we first map it to the tangent space of the origin. We perform this matrix multiplication in the tangent space. And because tangent space is Euclidean, this operation is well defined. And after we perform this linear operation, we can then map it back to the hyperbolic space through this exponential map. So compared to the Euclidean operation, basically it adds this exponential and logarithmic map to convert to and from the tangent space to perform this operation. And similar is also true for addition, but here we need to have a special operator called parallel transport, which tells you how to move the vector around in the space. So this might not seem very intuitive, because in Euclidean space, a vector can be moved around the Euclidean space without affecting its length. But actually in hyperbolic space, you cannot freely move the vector, because as you can see in the visualization, if we move if we move a vector out towards the edge of it, it will seem smaller, right? The coordinate will, the norm of that vector will have to change. So there's this also the parallel transport here. And that represents the analogy of the addition operation in the hyperbolic space. And all these, notice that all these functions, although they are very complex, are differentiable. So we can also use PyTorch and any auto differentiation software to perform these operations. And in the aggregation, this is basically very similar to graph attention networks that we have learned. So we have this attention weights here, and we also map the points to the tangent space, use the attention weights to aggregate them, and then again map it back to the hyperbolic space. And in the update function, it again follows the same rule, where we map it to the tangent space, we perform the nonlinearity, but note that here we are mapped back to a different curvature, right? Because the next level has a different curvature and different space definition. So finally, just to show a little bit of results, here we can see a GNN embedding of a tree-like structure. And as you can see, because there are exponentially many points in the space, and the geometry is not very nicely preserved, because here we visualize the nodes as like the lighter blue nodes represent the leaves, and the dark blue nodes represent the root. And you can see that some of these leaves are actually embedded very close to the root, which does not respect the tree structure. Whereas in the hyperbolic geometry, using the hyperbolic GCN, we're able to recover this tree-like structure very nicely, and all the points are embedded in their respective hierarchy. And we also discovered that curvature is very important, and there is a sweet spot where we can embed the a tree with a low distortion, but also very stable, numerically very stable. And finally, we also evaluated in a bunch of other standard data sets, graph data sets, and we basically use this hyperbolicity to measure like how good is the hyperbolic GNN will perform in a given data set. So this metric can be found in this Gromov hyperbolicity paper. And basically, the lower the hyperbolicity, the graph becomes more tree-like. So here, for example, delta equals to 0. That means that the graph is kind of a perfect tree. Whereas here, if delta is 11, then the graph is not very hierarchical or not very tree-like. So we can see that the hyperbolic GNN will tend to perform very well or extremely well when hyperbolicity is low. So which means that the graph is very tree-like. Whereas if the graph does not look like a tree, then the performance tend to drop. So that's why the hyperbolic GNN is especially suitable for hierarchical and tree-like graphs. Just to summarize, here we introduced the hyperbolic geometry, and we have two models, the Poincare ball and hyperboloid model, to visualize and represent the hyperbolic space in the Euclidean as a subspace of the Euclidean space. And we can use exponential and logarithmic map to map points to and from the tangent space, which is Euclidean, where neural network operations can be performed. And finally, we show that we can use a learnable curvature at every layer of the GNN, so that we can trade off performance and stability. Thank you, and that's all for this product content.